Okay, so for today's lecture, we're going to talk about statistical significance and hypothesis testing. You might remember the term statistical significance from when you took Psych 42. So we're going to have a bit of a refresh on that just to kind of make sure you guys understand or able to, you know what it is to have statistical significance and how we make these claims by using null hypothesis testing. So we'll start with the difference between descriptive and inferential statistics. So with descriptive statistics, it's very surface level, very basic. It's pretty much asking what happened, what does our data look like? Whereas inferential statistics is kind of getting more into the meat and potatoes of, okay, so we know what the data looks like. What does this tell us about the bigger picture? So I like to think, I like to use the analogy of descriptive and inferential statistics by saying that descriptive statistics are, if you're trying to get to know someone, descriptive statistics is just looking at what it is they look like. So maybe what they're wearing, or what, color eyes they have, what color hair do they have. That tells you something, right? Okay, so you're a blue-eyed white woman with brownish, blondish hair, and you're wearing a flowery shirt. Okay, so that tells you something. That tells you what I look like. That tells you kind of a basic gist of what it is I'm presenting to you. But inferential statistics, that would be descriptive statistics. Inferential statistics is getting more so into what is your personality traits? How do you treat your friends and family? It's deeper, that you kind of have to get in a little deeper than just surface level to really understand. You don't know someone is a total asshole by just looking at what they're wearing, unless they're wearing a shirt that says I'm a total asshole, but that defeats the purpose. So you don't really know a lot about a person just by looking at what they look like. Just how you don't really know everything about the data just by seeing the means and standard deviations, which is descriptive statistics. You can have an idea by using these things for analysis, and we'll get into that a little later. But ultimately, inferential statistics is really getting into your hypothesis, what you're anticipating to happen. Oh, I think people that take an exam in a quiet testing condition will score higher than people who are taking it in a loud and distracting testing condition. Well, the means and standard deviations, like, oh, the quiet testing condition had a mean of 77 and a standard deviation of 5, where the loud condition had a mean of, 72 and a standard deviation of 4. That is descriptive statistics. It's all fine and dandy, and you definitely need to have that. But inferential statistics is saying, okay, I'm going to conduct an independent samples t-test, and I'm going to determine if these sample means that I have, the 77 for the quiet and the 72 for the loud, did this happen by chance? If I were to give the same exam to 50 different people in each group, if we had 50-50, would they get, are these means just a fluke? Are they by chance that they just happen to be this far apart or this close together? Or is there something that we can actually infer about the population here? Is it saying that, hey, if you take a test in a quiet condition, you will, or it's likely, I guess, that you'll score higher. It's proven, it's shown through this empirical research that we've conducted that quiet testing conditions tend to fare better in terms of test scores than do noisy testing conditions. So the fundamental question of null hypothesis testing, is, does the effect we have on our sample, is this difference between our loud and quiet group, our loud group had a mean of, let's see, let's write this down so I can actually remember it. Okay, so our quiet testing condition had a mean of 77 and a standard deviation of 5, and our loud testing condition had a mean of 72 and a standard deviation of 4. These differences in our samples here, this mean 77 for quiet, mean 72 for loud, and the appropriate standard deviations, is that something that happens in the population? So if every person that takes an exam in a quiet testing condition compared to every person who takes a test in a loud testing condition, are we going to see this? Are we going to consistently see that quiet performs better than loud consistently? So is this something that is reflected in the population? Everyone who takes, or at least, some people, and that's why we have standard deviations. There's always variability. It's not like every single person who takes a quiet exam is going to perform better than every single person who takes a loud exam. Maybe some people in a quiet condition, maybe they have ADHD and they kind of can't focus when it's quiet, or maybe it's the opposite. Maybe they can't focus when it's loud. Maybe people are just more used to testing in loud conditions. But overall, as a whole, does this effect of the quiet condition testing considerably higher than the loud condition? Is this something that's reflected in our population and not just in our sample of 50 and 50? 50 in the loud, 50 in the quiet. Do these 50 people who take the loud test perform worse than the 50 people who perform the quiet test? And is this something that if we were to give it to every single person, would this be a consistent factor? So it's by chance. So when we say, oh, did this occur by chance? Did quiet condition just by chance score better than the loud condition? We're testing for that. And by chance, that's saying, is there a sampling error? Maybe if, these 50 and these 50 people in both of our conditions, these were their means. But if we were to take 50 different people and put them in the loud condition and 50 completely different people and put them in the quiet condition, would they have this same stark difference between them? Or would they be closer together? Maybe the means are like 75 and 72, or, 75 and 74. I don't know. So sampling error could just can be attributed to just different people taking this. Maybe it's just those 50 people in each of our conditions, 50 in loud, 50 in quiet, 50 different people, I should say, in each condition. Is this big difference we found just because of these 100 people total, or is it something else? Or is it that there really is a difference? That's a sampling error to say, oh, it's just these 100 people total just happen to perform this difference. They just happen to have this big difference. But when we tested this over and over and over again, there really wasn't much of a difference between the loud and quiet conditions. So when our population means are equal, so to say, oh, sampling error, oh, there's going to be some variability in our samples here. When we say that our populations are equal, so if we were to take the population of everyone who took a loud test and the population mean of everyone who took a quiet test, if they're equal, chances are when you select samples from both of those populations, they're not going to be exactly the same. You can have the population means be fairly similar, not much of a difference between them. But if you were to take, it's bound that you're not going to get every single person performing like the exact same score. There is going to be some variability. Some people will score 70 within our 50 people. Some people will score a 75. Some people might score really well and do a 90. Some people might do 50. And that part just depends on, well, what is it they're being tested on? What is the individual characteristics of people that can attribute to the sampling error? So even if there is no difference in the population, even if we were to even if the population of loud and quiet test takers were equal, if we were to take samples and compare them, they would still be different. And what we're saying by, oh, did this occur by chance? If we do not have statistical significance, to say that, oh, well, we do have differences in our samples, our one means is higher than the other. But our populations are equal anyway. So that was kind of bound to happen, because it's not like we're going to get 50 people in each group and each individual person will be matched with exactly the same score. There is going to be some variability, even if the populations are fairly similar. So to use inferential statistics, we use the normal distribution. You might remember this from statistics from Psych 42. This is a breakdown of the normal distribution. You might remember the 68, 95, 99.7 rule, also known as the empirical rule. But this here that we see is a normal curve, a normal distribution, and it is where the 0 is our mean and a standard deviation is equal to 1. So when we go 1 standard deviation below the mean at that -1, again, that's just a standard deviation below the mean. That's not saying that our standard deviation is equal to -1, because we can't have a negative measure of variability. But if we were to go 1 standard deviation below the mean, so from that -1 to 0 area, you see that 34.1%. That's saying that in a normal distribution of a population, 34.1% of that distribution, of that whole population, 34.1% is going to be between the mean and 1 standard deviation below. And then the opposite is true for from 0 to 1. 34.1% is going to be between the mean and 1 standard deviation above. So when we have this 68, 95, 97, 99.7 rule, it's saying that 68% of the data lies between 1 standard deviation above and 1 standard deviation below the mean. That's just adding our 34.1 to 34.1. And that we're rounding it, so it's 68% instead of 68.2. But we have, 68% of a normal distribution is going to be between 1 standard deviation above and below the mean. And then as we branch out, then it gets to 95%. So now we're just adding all of the numbers between -2 and +2. So 13.6 plus 34 plus 34 plus 13.6. And that gives us approximately 95. So that's where these numbers are coming from for the 68, 95, 99.7, also known as the empirical rule. So it's real, the normal distribution is real, but it's also theoretical. So when we have populations, typically they don't really follow a normal distribution. Because a normal distribution is absolutely symmetrical. If we were to fold that in half, it would be perfectly lined up. It is going to be, equal sides on each half of the mean. A normal distribution. It's perfectly symmetrical. However, that's more so theoretical, and it's not necessarily real world application. However, many distributions will approach a normal distribution if they're large enough. And so typically we tend to use, since this is true, since many distributions will approach a normal distribution, we use the normal distribution in order to make our claims when we do inferential statistics. So this is known as the central limit theorem. If you remember Psych 42 talking about the central limit theorem, where basically it will approach normal. So this normal distribution gives us a sense of the expected distribution of scores and how likely a certain score will be. So when we say, the average score in one condition is significantly higher than the average score in another, we use the normal distribution in order to really say, well, what's the likelihood that if we were to say, we always assume there's no difference in the population. So using the normal distribution, we can say, how likely is it that if we're going to assume that there's no difference, how likely is it that these samples are what they are? If they're really equal, why is this sample so much larger than the other? Maybe because they're not equal, but we have to start with the assumption that they are. But the normal distribution, in a nutshell, is what we use to make these claims in inferential statistics. It's how we determine statistical significance. It's the theoretical framework of, do we reject or retain the null hypothesis? Is there a difference between students who take a test in a loud condition versus students who take a test in a quiet condition? So I've said this word a lot, these words, statistical significance. So it's the term when a result is not likely due to chance. So this is where if we find a difference in our groups and it's substantial, we say, there is statistical significance. So it's saying that, hey, the population of all people who take a loud test versus the population of all people who take a quiet test, there's a difference here. And if we have statistical significance, we say it is not due to chance. It's not just because these 100 people that we have in 50-50 in our loud, 50 in our quiet, they just kind of stumbled upon accidentally having the quiet having a higher average than the loud. No, to have statistical significance would be saying, no, dude, people who take tests in a quiet condition, they really do perform better overall than people who are going to take tests in a loud condition. So we use p-values, which is essentially just a probability, to determine statistical significance. We take any inferential test that we have provides us a p-value. And this p-value is just the probability of, if our null hypothesis is true, it's the probability that we would get this sample that we have. We would get this sample mean of 77 and 72 when it comes to loud and quiet testing conditions. The lower your p-value is, the lower the probability that your null hypothesis is to be retained, that it's true. So when we have hypotheses, when we're thinking, oh, I think that I'm going to perform an experiment and I'm going to put 50 people in a loud testing condition and 50 people in a quiet testing condition and see which does better, you want a low p-value because you made this hypothesis of saying, ooh, quiet will perform better. So if you have a low p-value, that's saying, hey, people who take tests in a quiet and a loud testing condition, they're not going to perform the same. So that's what you're thinking. That's what you're saying, that quiet will perform better. So instantly your hypothesis is saying, they're different. So we use different ways. So in order to gain this information about statistical significance, we need to have our descriptive statistics. You'll see here this example of, oh, there was a significant difference in average moral judgment between participants with science terms with a mean of 6 and a standard deviation of 2, and those in a control condition with their means and standard deviations. So you'll see that, oh, when we make statistical significance, when we perform inferential statistics to help us determine if we have statistical significance or not, this is how we might report it. And we need descriptive statistics not only to report it, but also we need those to plug into our formula to, conduct our appropriate inferential tests. So with significance level, I've talked about p-value, and basically the lower it is, the less likely that your null hypothesis will be retained. However, we can't just say that willy-nilly. We do have a threshold in which we say, okay, if it's less than this value, then we have statistical significance. If it's greater than that value, we don't. They're approximately the same. So our alpha, this is our significance level is our alpha. That is our threshold to say if it is below alpha, if our p-value is less than alpha, then we have statistical significance. If our p-value is greater than alpha, then we don't. We do not have statistical significance. So we are going to be using depending on your projects, you might be using an independent samples t-test, a dependent samples t-test, but regardless of what kind of test you're using, most inferential statistics, if not all, they all do actually, all inferential statistics are using p-value to determine significance. So we have this p-value of, we did our t-test and our independent samples t-test for our loud and quiet conditions with 50 different people in each condition, and our p-value is 0.002. Well, we also need to say, okay, so there's a 2% chance with a p-value of 0.02. You can translate that 0.02 to percentage, which would be 2%. Where is it? Okay, right there. So you can say, oh, there's a 2% chance that our null hypothesis should be retained. There's a 2% chance that if these means if these populations of people were really the same, if people who take loud tests in loud conditions and people who take tests in quiet conditions really are the same, the likelihood that we got these results, the 72 mean and a standard deviation of 4 for loud, and the 77 mean with a standard deviation of 5 for quiet, there's a 2% chance that we would get these results if these two populations tested the same way. So if there wasn't a difference between quiet and loud testing conditions, there's a 2% chance that we would get these particular results. However, like I said, we use alpha to determine if we will retain or reject the null hypothesis. Typically, alpha is set at 5% or 0.05. However, it can be, typically alpha is determined. So if you're going to be saying, oh, I'm going to conduct an independent samples t-test, I'm going to set my alpha at 0.05, we know, okay, so if our p-value is less than that 0.05, then we will reject the null hypothesis. And if our p-value is greater than 0.05, we will retain it. So in this case, let's say that our alpha for this problem is 0.05. Alpha alpha refers to the Greek letter alpha. So whenever I draw it, it always looks like a Jesus fish. So I kind of jokingly refer to it as Jesus fish. But if we have our alpha for this problem set at 0.05 and our p-value is 0.02, we would reject the null hypothesis because our p-value is less than the critical significance value that that we're using. Our p-value is less than 0.05, so we do have statistical significance if this is what we have. So we would reject the null, and we have statistical significance. Okay. So boom, here we go. Just to kind of spell it out. So we have rejected the null hypothesis here. Oh, wait, no, here. We've rejected the null hypothesis, and this means that we have statistical significance. And again, we've made this decision based on the fact that our p-value of 0.02 is less than our significance level of alpha, which is 0.05. Now, this can easily change. If we were to change our alpha value to 0.01, which is another, it could be, that is another alpha value that people use. If we set our alpha value at 0.01, then actually we would not have statistical significance because our p-value is greater than alpha. So in that case, we would not reject the null, and we do not have statistical significance. I'm not going to write upside down because that's just going to be atrocious. But if we have our alpha at 0.01 and our p-value is 0.02, then we would retain the null hypothesis because our p-value is greater than alpha. So as a bit of a refresher on main effect and interaction, so when we have multiple independent variables, we can have a couple different results. Now, with our loud and quiet testing condition, we only had one independent variable, with loud and quiet being our conditions, and the independent variable itself just being, hey, these are our testing environments. Are you in a quiet or are you in a loud testing condition? So with a main effect, that's just essentially testing what we just did. So a main effect is just looking at a single independent variable. So in our case, testing conditions. Testing conditions. And that's going to be loud or quiet. Okay, so with our independent variable of testing environment, testing conditions. Our independent variable over here is testing condition. Are you in a quiet or a loud one? I don't know how to do that. Okay. Okay, that is testing for a main effect. That's just one single independent variable and comparing the two groups within them. With an interaction, that is looking at a combination of independent variables that has some type of effect. So maybe we do the same thing. Maybe we have people in a loud testing condition and a quiet testing condition, but some people are, so that's one independent variable. Which testing condition are you in? Which environment are you taking your test in, loud or quiet? And then we have another testing condition where we're providing people silly hats and we're not providing people silly hats. So maybe people in the quiet testing condition perform better than people in the loud testing condition, but only when they were wearing those silly hats. They only did better when they wore the hats. That would be an interaction because we have our independent variables of testing condition, group A and group B, and then we have our second independent variable of, are you wearing a silly hat? Yes or no. So silly hat wearers and no hat wearers. And then we compare. And if we see that, oh, well, people in the quiet condition only did better than group B and when they wore these hats, that would be an interaction because it's just kind of taking into account two conditions of two separate independent variables and how much better they perform or how much worse they perform due to those conditions. Okay, so here's an example question. So a researcher has an alpha value or alpha level of 0.01. So alpha is set at 1%. The researcher conducts an experiment on water retention and the type of food eaten. The researcher said that there was a main effect of type of food on water retention with these are their T results, their T test results. So T with their degrees of freedom of 2,746 and their test statistic of 12.734 with a P value of 0.034. So the researcher says that water retention was affected by the type of food ingested. Is the researcher correct? So this is a main effect because we only see one independent variable conducts an experiment on water retention and the type of food eaten. So the type of food eaten is going to be the dependent variable. So there is only a main effect here. We don't have more than one independent variable here to be dealing with. We only have water retention. Okay, so we do know that this is a measure, this is a question of whether or not there is a main effect. So now we have to look into the rest of the question. Okay, so our p-value, they're saying that water retention was affected by the type of food ingested. There was a main effect. So for there to be a main effect, we have to have statistical significance. So that means our p-value has to be less than alpha. So our p-value here, to have a main effect, our p-value is 0.034. Okay, cool. And our alpha value is 0.01. Well, since our alpha is set at 0.01 and our p-value of 0.03 is greater than that, we do not have statistical significance. We would actually retain the null hypothesis when we have an alpha value of 0.01 and a p-value of 0.03. So is the researcher correct when they say that there was a main effect on the type of food eaten or on the type of food and water retention? No, the researcher is not correct. If they set their alpha at 0.05, they would be. But since their alpha is at 1%, since it's at 0.01, their claim of having a main effect in this problem, in this experiment, is incorrect. They do not have statistical significance. They do not have a main effect. So with a hypothesis, moving on. So a hypothesis is different from a research question, but it is developed from one. So you might think, I wonder if pineapples grow faster in humid climates or dry climates. Your research question is kind of what you ponder. It's like your shower thought, I guess. Your hypothesis is kind of pulling the trigger on, okay, what do I think is going to happen? I have the question of, do pineapples grow faster in humid or dry climates? But my hypothesis is going to say, there's going to be a difference in pineapple growth and how much these pineapples grow depending on where they were grown, be it the humid or the dry. So we use this hypothesis to infer results of a sample to a population. So we use the hypothesis of pineapple growth. There's a difference in pineapple growth depending on where you grow it, be it in a humid or dry environment, in a dry or humid climate. We use that hypothesis to, okay, now we're going to conduct an independent samples t-test. We're going to grow pineapples in a humid condition and a dry condition, or a dry and humid climate, and we're going to measure their growth by millimeters or inches, or I don't know, however pineapples grow. I guess millimeters. I don't know. But we're going to measure their growth using some type of, form. So we're going to operationally define our dependent variable of growth by millimeters, let's say. Or no, let's do centimeters. Millimeters seems a little small. But we're going to measure it by centimeters. And we're going to see if there is a difference between dry climate grown pineapples and humid climate grown pineapples. And so what we're going to infer from this test, from this experiment of taking, 50 pineapple seeds and planting it in a humid condition or a humid climate, and 50 pineapple seeds and planting them in a dry climate, is we're going to see, hey, is there a difference in pineapple growth depending on if they're grown in a dry or humid environment? So I mentioned the null hypothesis before, and how we always assume that it's true, and how a p-value is just the probability that your null hypothesis is true. So with that, let's kind of break down null hypothesis. So we've talked about how a hypothesis is just your expected outcome, what you think would happen. Like, oh, there will be a difference in pineapple growth depending on where it is they're being grown, be it in a humid or a dry climate. Null is saying, and the word null is just means like no change, no difference, nothing to see here, officer, whatever, nothing. So a null hypothesis is saying that these two populations that we're testing for, with pineapples grown, all pineapples grown in a dry climate and all pineapples grown in a damp, humid climate, a null hypothesis is saying there is no difference in the growth between there is no difference in growth between these two climates. They're going to be the same. We always assume this is true when we go into an inferential test, when we go into an independent samples t-test, a dependent samples t-test, ANOVA. We always assume that the populations in question are equal. We assume, okay, dry, humid, doesn't matter where these pineapples are going to grow. They're going to grow at approximately the same rate. Our alternative hypothesis is saying, hey, there is going to be a difference in the pineapple growth depending on where it was grown. So what the researchers' hypothesis, there's going to be a difference, and think of your hypothesis for your projects, there's going to be a difference in this and that based on this or whatever. Your hypotheses that you guys come up with, your things that you're expecting to have happen in your projects, that is your alternative hypothesis. Whereas the null is saying, nah, they're the same. Your hypothesis is saying, nah, they're different. So by doing an inferential test, in this case, let's do an independent samples t-test. Again, we're taking 50 pineapple seeds and planting them in a humid environment, and 50 pineapple seeds and planting them in a dry environment, and measuring the growth in a, 6-week, 6-month span. I don't really know the life. I don't know like when a pineapple reaches full maturation, but we give it a period of time and we measure the difference in the growth. And then after we've measured the growth, on a day-to-day basis, or find the overall average growth over 6 weeks or something, we compare these using an independent samples t-test. And by doing that, then we can decide, are we going to retain the null hypothesis or reject it? So you'll see that retain is also known as fail to reject the null hypothesis, but I feel like it's a little wordy. So I like just kind of saying retain the null hypothesis. We're holding on to it. If you retain water, you're kind of holding in water. So if we retain the null hypothesis, we're holding on to it. We're saying, yeah, we're going to keep it. You know, we're saying that there is no difference in our populations here. So inferential statistics is telling us, are we going to retain or reject the null hypothesis? If we retain it, that's saying the populations that we're testing here are approximately the same, and any differences that we saw in our samples are due to chance, just because these 50 pineapple seeds just happen to grow at this rate. Those 50 pineapple seeds happen to grow in this rate, because we're likely not going to have the exact same growth just based on, you know, if you take a stats test, or if you take a 144 test, or hell, if you are a fantastic basketball player, let's say, and you are taking 100 shots, 100 free throw shots, let's say, you're, you know, you got fouled 100 times, well, maybe like, okay, anyway, if you take 100 free throw shots and you're a great basketball player, chances are you'll probably get in like the 80 to 90% made region. But sometimes you might, you know, sometimes you might get 90 out of 100. Another day you might get 89 out of 100. Another day you might get 93. Some days you might kind of fuck up and say, oops, I got a 72. Holy shit, I need to work on it. That's Shaquille O'Neal. But ultimately, it's still, you're not always going to get the exact same every time. So that's kind of what I mean by saying, even if your populations are equal, even if you would retain the null hypothesis, your samples will be a little different just based on, you know, just the difference. That there's just going to be your variability in your samples. That's just how it is. You're not always going to shoot a 90% free throw rating every time you hit the court. You're probably going to average to that, but it's not like every time you take 100 shots, you only make 90 every single time. There's going to be some variability there. So, long story short, we have, I actually didn't mention confidence intervals. So when we have a p-value, or when we have our alpha set at 5%, let's say, we have a confidence interval of 95. We have a 95% confidence interval. If we have an alpha value set at 0.01 at 1%, our confidence interval is 99%. So it just fills up to 100. Whatever your alpha is, if your alpha is 10%, your confidence interval is going to be 90%. If your alpha is 5%, 95% confidence interval. Anyway, but this is a confidence interval. That's saying that this is our percent confidence that the results we have are true to the population. So we reject the null hypothesis if, again, our p-value, the probability of our results, are below that threshold of alpha at 5% or 1% or whatever. And we retain it or fail to reject it if the probability is above alpha. So the null hypothesis is not only, we're using the samples to make these claims, but the null hypothesis itself is referring to the population. When we say, oh, we're going to retain the null hypothesis, that's saying that all pineapples grown, remember our null hypothesis for the pineapples was that there's not going to be a difference regardless of where you grow them in a humid or a dry climate. The null hypothesis, when we retain it, is saying, okay, so for all pineapples grown in humid or dry conditions, it doesn't matter. All these pineapples will grow at approximately the same rate. So we use the samples to determine whether or not we'll reject or retain the null hypothesis, but the null hypothesis itself is in reference to the population or populations in question. So the alternative hypothesis, also known as the research hypothesis, is just what you think, what the researcher is thinking will happen. And then how likely it is that we'll get these sample means of, you know, we had our 72 and 77 for our loud and quiet, let's say. How likely it is that we would get these sample means if the null hypothesis were true is the p-value. So that's why we have this alpha set at 5% or 1% or whatever. If our p-value falls below that, that's saying there is a 2% chance that this happened there's 2% chance that this would happen if the null hypothesis were true. If these populations that we're measuring by these samples, if they were indeed equal. So we're human, let's not forget. So we make mistakes, and there's always going to be the possibility of an error in a null hypothesis test. So obviously, your null hypothesis can be true or false. We can retain it, we can reject it. Typically, when it's true, it is, we're retaining it. When the null hypothesis is false, we're rejecting it. But we're human, and errors can occur for one reason or another. So a type 1 error is saying, hey, we are rejecting a true null hypothesis. Here, let me get this. Let me write this out. And then a type 2 error is that we are failing to reject or retaining a false null hypothesis. So essentially, there are 4 choices. Whenever we have hypothesis testing, there are 4 choices you can do. You can either retain a true null, which is what you want to do. When you retain it, you're keeping it. And if it's true, that means you want to keep it. So you can either retain a true null, good, that's what you want to do. Or you can reject a false null. Cool, that's also what you want to do. If you want to, if the null hypothesis is false, you don't want to keep it, you want to reject it. If your boyfriend cheats on you, you want to reject him. You want to leave him. Okay. Anyway, that got weird. But those are 2 options out of the 4. Now, of course, the other 2 options of the 4 options is that you mess up. So again, a type 1 error is saying, hey, we're rejecting a true null. And a type 2 error, type 2 error is retaining a false null. Basically what you don't want to do. So with type 1, you're saying that there was a relationship or there was a difference when there is none. There is a difference when there is none. And a type 2 error is saying the opposite. You're saying that there's no difference when in fact there is a difference. Okay. So here's a little thing. So with a type 1 error, that's a false positive. Again, you're saying that there is a difference in the population when there actually isn't one. So that would be like telling a cis man that you are pregnant. You are not pregnant, dude. That's a false positive. There's no way if you are a typical, or I guess a cis binary man, that you are going to be pregnant. You just don't have the parts for it. So a type 1 error is telling a cis dude, you're pregnant, man. You better take some vitamin B because you need to keep your uterus happy. Yep. Anyway. So that's a type 1 error, if you want to think of it as a false positive. Telling a dude he's pregnant, that's a type 1 error. You're saying you are pregnant. There is a difference. There is a relationship. When in fact there is none. You're not pregnant, man. But I'm going to tell you you are. That would be a type 1 error. A type 2 error is a false negative. So you're saying that there's not a difference, or there is no difference in the population here. There is no relationship, nothing to see here, when actually there is one. That would be like watching a woman's water break, as if you're pregnant and your water breaks, and that tends to let you know, hey, it's go time. That would be like watching a pregnant woman's water break and saying, oh, you just peed yourself, or like, oh, you're not pregnant. Whatever. You're saying that there is no difference when there actually is. You're saying there's no relationship when there actually is. It's a false negative for a type 2 error. So yeah, if that helps you kind of break that down. Type 1 error, you're telling a cis man he's pregnant. That's a false positive. A type 2 error is a false negative, telling a pregnant woman you're not pregnant. You're saying there is no difference when there actually is one. There's no relationship when there actually is one. So to put that into context, to put that into some questions, so which of the following is an example of a type 1 error? Is it said people don't like kale even though people don't like kale? Said people don't wear garbage even though some people wear garbage? Said people breathe oxygen even though people do breathe oxygen? Or is it that you're saying that people live in the center of the earth even though people don't live at the center of the earth? So I'll give you guys a second to kind of think about it. So again, I stated how there are 4 options when we're doing null hypothesis testing. You can reject a false, you can reject a true, you could retain a false, you could retain a true. 2 of those are correct. So when you say that people don't like kale, even though people don't like kale, okay, that works. That would be that would not be an error. You said people don't like it, and people don't like it. That would be correct. You say people don't wear garbage, even though some people wear garbage. Okay, that's an issue, so let's keep that in the back of our heads. Let's go on to C. Said people breathe oxygen, even though people do breathe oxygen. Okay, that's all. That checks out. And now said people live at the center of the earth, even though people don't live there. Okay, so we know that A and C, those are correct statements. You did the right thing if that was your null hypothesis test. If you do either A or C, you were in the right category of you didn't make an error. It's either B or D where we have to look into this. So with a type 1 error, all right, you're saying that there is a difference when there actually is none. You're rejecting a true null hypothesis. So if you're thinking that people live at the center of the earth, even though people don't live at the center of the earth, versus, oh, people don't wear garbage even though they do. When you say there is a difference when there actually isn't, when there is a relationship when they actually don't, that would be D. You're saying, again, type 1 error is there is a relationship when there actually is none. You're saying people do live at the center of the earth when people don't live there. They would die. They would turn into liquid hot magma. You know, a type 1 error is D. Saying that people live at the center of the earth, even though people don't. Telling a dude that he's pregnant, a cis binary man that he's pregnant, even though there is no way he could be, etc. That's a type 1 error. Now a type 2 error, I just click forward, it's the exact same question, except now we're pointing out the type 2 error. So here we have, again, retaining a false null. We have that there is no difference when there is one. You're saying there's nothing to see here when there actually is something to see. That would be B. You're saying people don't wear garbage, even though you literally walked past someone who was wearing banana peels or something. I don't know. So that would be like telling a pregnant woman after her water just broke, oh, you're not pregnant, you're okay. That's just, you just have some problems keeping it in. Maybe don't drink so much tea and coffee or whatever. I don't know. So a type 2 error would be saying that people don't wear garbage, even though people do. There is no relationship saying, nope, nobody wears garbage, nobody, nope, when actually you're saying the opposite, when actually the opposite is true. So a type 2 error would be B. People don't wear garbage, even though people do. Okay. So there are different things that matter in hypothesis testing. Sample size and effect size. So effect size, the larger effect size we have, larger effects are less likely to be due to chance. So the larger your effect size, the more likely it is that there is something real happening there in the population. Again, effect size, what we've covered so far with effect size is Pearson's R and Cohen's D. The larger, the bigger the strength is, the larger the effect is. If your Cohen's D is, 1 when a 0.8 is considered strong, or if your Pearson's R is a 0.7 when a 0.5 is considered strong, that would say, hey, it's likely that that's reflecting of the population. However, that also coincides with the sample size. So when we have larger samples, this also reflects a better idea of what the population is really telling us. So if we take a sample of, if we were to do Cohen's d, which is comparing the means of one group to the other and seeing how many standard deviations they differ, how many pooled standard deviations differ between them. If we were to conduct that, and we looked at the average for one group is 5 and the average for another group is 10. Ooh, damn, that's going to probably be a big Cohen's d because our means are pretty different. Maybe the standard deviation is like 2. Oh, okay, cool. We have a Cohen's d of, okay, 5 minus 10 is -5. And then our pooled standard deviation, let's say both standard deviations are equal to 2. So our pooled standard deviation, aka the average of the standard deviations, is 2. So, oh, -5 divided by 2 is -2.5. That's a strong Cohen's d. Wow. The difference in the population, ooh, if we're just looking at effect size, it's probably pretty strong. That's a pretty large effect size that we have there. However, you also have to take into account the sample size. So given that same problem, if we have Cohen's d of -2.5, however, in total, we only had 20 people, 10 in each group, you probably need to get a little bigger of a sample size because your sample size needs to be a decent size in order to actually better reflect the population. It would be like if I had a small sample size, who knows who's going to be in my sample. So if I had to take two random scores of the class, let's say of the overall class, of all the points that you have earned in this class up to this point, if I were to take just 2 students and find the average between them and say, okay, every single person has that grade now, that could either go really well or really shitty. I can take 2 A students just by chance and like, okay, everyone gets, 90 and 90. Everyone gets a 90. Oh, yeah, cool. Oh, yeah. But that's not really reflective of the population of your grades as a whole. What if I were to take 2 F students and then now everyone has an F? Well, that's not fair. So the larger your sample size is, the better it reflects the population. Now, if I were to take an average of the whole class and say, okay, I'm going to take your average points, each person's points, and average them together, and there's, X amount of points. Now everyone has that grade. Well, I wouldn't actually do that. That's terrible. But ultimately, it's like, okay, that would be a better reflection of the population. That would be a better reflection. Or maybe let's not even say I'm going to give you guys that grade. If I were to just take, oh, what's this class understanding at this point? I'm going to see I'm going to select 2 students and see what their test scores were. Oh, I got 2 A students. Oh, well, the average test score was 90%. Oh, everyone in the class must understand research methods. Tee-hee, woohoo. Well, that wouldn't be very accurate. So the larger my sample size is, maybe instead of 2 people that I'm taking who happen to be A students, or maybe 2 of them happen to be F students, wow, no one gets it. I better dumb this down. Okay, 2 plus 2, guys. Like, that wouldn't be reflective either. But I need to take a larger sample size for me to get a better idea of where your understanding is as a class in terms of research methods. So I would probably take just the whole damn class's average and then say, okay, so the average is a 77 or whatever the case may be. Okay. Doing pretty good. That's a pretty decent base there. But ultimately, we need to have both factors involved. We need to have sample size because the smaller it is, we need to have larger ones to reduce the error. We need to have larger sample size to ensure we kind of get as far away from making errors and mistakes as possible. So if you have a really small sample size and you're saying, oh, everyone, our 2 people got 90%, so that's our average, everyone gets it. Ooh, that's a gross misunderstanding. That's a terrible mistake you just made to think that everyone understands it because you just took the average of 2 people. You need to take the class average. You need to increase your sample size. And then the effect size, again, the larger ones are more likely to be less likely, to be due to chance. So if you see massive differences, if you see an effect size of, again, -2.5 for your Cohen's d, That's saying, ooh, these two groups are probably not that equal. But that also takes into account, do we have a decent sized sample? Okay, so both of them go together. So with intuitive hypothesis testing, this is not really, it's like quick and dirty hypothesis testing. We don't get p-values from it. We're not really calculating the inferentials here, but it's just kind of at the surface, is it significant or not? So we do this by analyzing the relationship strength and the sample size. So why do we do this? Well, it kind of helps us understand hypothesis testing a bit. It helps us understand effect size and the importance of a larger sample. And it also allows us to, when we actually do conduct the hypothesis test, the formal hypothesis testing, then it's like, oh, well, looking at it, it kind of looked like it wouldn't be significant, but it is. Did I make a mistake, or did I put in a wrong number somewhere, or did I kind of miscalculate this, or what's going on? So it allows for problems for error detection, so kind of checking your own work, and also allows you to say, oh, looking at this, I can understand that there's probably going to be a difference here because we have a large sample size as well as a relationship strength of X, or whatever. So with an example, we're taking into account, again, sample size and effect size. I can't apparently erase and talk at the same time, but this is a well-known fact for me. But anyway, so what we do is, let's look at this first example. So group A with a sample size of 100 has a mean of 34. So group A, mean of 34, and a standard deviation of 5. And then group B, again, sample size of 100. So group B, mean of 39, and a sample size, or standard deviation of 5, and a sample size of 100. Okay. So first, again, we have to look at sample size and we have to look at effect size. So our sample size total is 200. Group A and Group B all together have 200 people. Okay, so far, so good. We have a pretty decent sample size. I would say that would probably reflect the population. That would probably reflect what we would expect to find in the population. Now, the question remains to, well, what is the effect in the population? Is this going to be a strong, medium, or weak effect in the population? Well, to do this, we have to calculate the effect size. So when we're comparing the means of two groups, we have to do Cohen's d. So this is taking the mean of group 1 or group A, so 34, and subtracting it by the mean of the second group. So 34 minus 39 divided by the pooled standard deviation. So the pooled standard deviation here is going to be the standard deviation of group 1 or group A plus the standard deviation of group B divided by 2. Again, it's literally finding the average of the standard deviations. So 5 plus 5 divided by 2 is 5. Okay, so our pooled standard deviation for this first example is 5. And so now we have 34 minus 39 divided by 5. So 34 minus 39 is negative 5 divided by 5 is negative 1. So our Cohen's d, Cohen's d is equal to negative 1.0, which is a strong effect size. Again, if our Cohen's d is, if the number itself is greater than 0.8, it's considered strong. Now the number 1 is greater than that. So, okay, here's what I've written out. Okay. So, is this significant or not? We have a sample size of 100 in each sample. So that gives us a total sample of 200. That's a pretty good sample size. And so with that being a good sample size, we can ascertain that anything we see, what we see in this particular problem, whatever our effect size is likely representative of that we will see in the population. So we have a sample size of 200, pretty good, and our Cohen's d is negative 1.0. So that's saying that, hey, whatever it is that we're looking at with these two groups, the difference in these groups in terms as a whole in the population of one group versus the difference of the population in the other, it's likely that that's going to be a strong effect size. There's going to be a strong or large difference in the population since we have a large enough sample size. Okay. So it would be significant. So is it significant? Yes, we have a large sample size. We have a Cohen's d of negative 1.0. So with that large sample size, it's saying whatever it is that our effect size is likely representative of that in the population, which is significant. So now this next one, n is equal to 24. Now that capital N is the entire groups. So with Cohen's d, Cohen's d is equal to 0.15. Keep in mind that for Cohen's d, we have two groups. So with our capital N equal to 24, and Cohen's d representing two groups, that means that we actually have approximately 12 people in each group, because that capital N is everyone altogether. Just like how that first example, our capital N was 200, because that's adding our sample of 100 to our sample of 100 for group B. So is that significant? Well, no, I would say it's not, because that sample size of 24 total people, when we're comparing the difference between two groups, as we do for Cohen's d, that's not enough people. So we cannot determine if this is not significant, because we cannot determine if that d is equal to 0.15. We can't say if that effect size, if that relationship strength is really indicative of the population, because we just don't have enough people to determine it. So the role of sample size should make sense. Like I was mentioning before, how if I were to take the average test scores for two people and say, this represents the class's understanding, versus if I were to take the average test scores for the entire class, a larger sample size, and say, this represents the class's understanding, it would make sense that we stick with the larger class size, or the more people in our sample that we're taking the means for. So for this example, which is more likely to represent a difference in the population? Both of the effect sizes are the same. They're medium. D is equal to 0.5. However, one has a total sample size of 20, so that's 10 in each group. And the other has a total sample size of 200, so 100 in each group. So again, kind of thinking about that class example, but on a much larger scale, it makes more sense to say, hey, the more people that we take in and do this, and we still find this strong effect size, hey, it's likely that this is something that really happens in the population in question. It's not just a fluke by these 20 people or whatever. It's not just those people happen to be really different from each other. It's the more people that we're testing, these 200 people, and we still have this large effect size. Hey, we're onto something here. Having a larger sample size should make sense in terms of saying we can apply this to a larger number of people, our population. So when we have larger samples, we have a greater confidence. We were able to better say our sample mean is close to the population mean. So the samples that we obtain, hey, or, it's closer to the population mean, or it's showing us the difference in the population means as well. So if we retain the null hypothesis and we have large sample sizes, that's saying, okay, so we're really seeing that this population, we're not really seeing any difference. Or, hey, this is really what the population represents. There's nothing here. And then the opposite is true. When we reject the null hypothesis, when we have large sample sizes, that's also providing us the confidence to say, hey, the means that we have really do reflect a difference in the population means. So overall, statistically, 100 in your sample size total, pretty good. That's a pretty good start. That's a good standard to have. even when we have large samples of 100 or 200 or whatever, that makes us confident that even if we have weak effect sizes, they're still going to be significant because we still have a representative of the population. We have enough people to say, if we have a sample size of 100, we have enough people to say, you know what? Even though this effect size is weak, we have a large enough sample to tell us that this weak effect size, this weak difference in the population or this weak difference that we have in our samples is reflective of the population. We have a big enough sample here. This does reflect the population. So don't let the Cohen's D or the Pearson's R being weak, small, medium, large, whatever, don't let that impact if it's significant or not. Think more so about the sample size. And when we have a large sample size, no matter how large or small our effect size is, when we have a large enough sample size, that is representative of what we see in the population. We will see, oh, if you have a sample size of 200 and Pearson's R is equal to 0.1, well, that's saying that our population the population of these two things we're looking at, the relationship between these variables and the population isn't very strong. That's okay. So the logic of null hypothesis testing is first we have to start with assuming there is no difference in the means of the population that we're looking at. So there is no difference between people who are going to be there is no difference in the exam scores for people testing in a quiet condition versus people testing in a noisy condition. We start with the assumption that they're going to test the exact same rate or have the exact same scores or averages or, close enough. Then next is we ask, how likely would the difference in my sample be? So this is where we have our alternative hypothesis and we're thinking, what is the likelihood that these will be different? We have to assume that they're equal, but what's the likelihood they're different? We compute the probability next, so we have our p-value. We compute that, and then we decide if our probability that the difference is there, or excuse me, if the probability that the difference that we obtained is due to chance, or if it's due to there's really a difference. If our p-value is less than 0.05, hey, reject the null. Cool. That's saying that it's not very likely if we do assume that there's no difference in the means. The lower p-value is saying, there's a 2% chance that this would have happened if we were going to go with that assumption that the means are equal in the population. So maybe we should reject that assumption. Maybe we should reject the null hypothesis here because there's only a 2% chance of the null hypothesis being true. So if we say that the difference is real by saying that the p-value is low, hey, cool, boom. And if our p-value is greater than 0.05, the difference that we found is just due to chance. It's just because these 50 people happen to test this way and those 50 people happen to test that way. The populations are still assumed to be equal, and only the differences that we found when we retain the null hypothesis by having a p-value of greater than alpha is just these people test a little slightly different. So here's some more terminology. We've already talked about these, but this is just kind of bringing it full circle. The null hypothesis, H naught as that is referred to, or that's what that is saying there. There's no difference in the population. Any difference that you see is due to chance. The alternative hypothesis, H1, is saying that there is a difference. And when you find a difference, when you obtain or retain the alternative hypothesis, is saying that the difference that we found is real. It's not due to chance. It's not because, it's a Tuesday and, if we would have taken any other 50 people, we would have gotten slightly different results, but they're still close. Alternative hypothesis is saying, nope, doesn't matter. You can take 1 million different samples of 50 different people. We're still going to find this to be true. We're still going to see that quiet tests consistently better than noisy or whatever. P-value is the probability of the sample result being of the sample result happening if the null hypothesis were true. So again, the lower your probability, the lower your p-value, the less and less likely that the null hypothesis is true. However, to determine statistical significance, we use alpha. That is where we say, okay, if our probability that the null hypothesis, if the probability that our sample result is, happening, if null hypothesis were true, if it's below alpha, then we say it's statistically significant. But if it's above it, even if it's like, a percentage above it, if our alpha is 0.05 and our p-value is 0.06, we're still going to retain the null hypothesis. It hasn't broken that threshold yet. So 100 men, here's another example. So 100 men have a mean score of 8 with a standard deviation of 2, and 100 women have a mean score of 10 with a standard deviation of 2. Do you think the p-value is going to be high or low? Well, this sample result would be unlikely if there's no sex difference. So first off, we have 160 men and 160 women. So we know that our sample size is large enough. That is 320 people total. We know we have that set. Okay. Now let's conduct our Cohen's d. Okay. So we have 8 minus 10, our mean of men minus our mean of women. So -2 divided by the average of 2, our standard deviations. So -1. So is p high or low? Low. The sample result would be unlikely if there was no sex difference. So the fact that we found this difference of Cohen's d of -1, that's a pretty large effect size. There's a big difference between men and women. So our p-value, the probability of this happening, is if there was no difference in the if there was no sex difference, is pretty damn low if we got an effect size that large. So just looking at this, again, p-value is retaining, or it determines if we have statistical significance or not. It's telling us, will we retain or reject the null? Just by looking at just sheer the effect size and how large it is, I'm going to say, just by looking at this at face value, I'm going to guess that the p-value is going to be low. The probability that this is happening is going to be low if there is no sex difference. So to compute the p-value, again, I said that we're going to do this for all inferential tests that we do. So what we have to do first is determine what's our inferential test we're using. Are we looking at a test? Are we looking at t-tests? Are we looking at ANOVA? So we need to determine which statistical test we're going to use and calculate the appropriate test statistic. We know how the test statistic is going to be distributed if the null hypothesis is true. We use that to then find the probability, and then that is how we pretty much find all null hypothesis tests. So every different test has a distribution. Every t-test, every ANOVA, any test statistic, T for t-test, F for ANOVA, has a distribution, and that is tailored to that specific test. We know that if it's rejecting or retaining the null hypothesis, it falls within that distribution somewhere. So we know how the test statistic is distributed when the null hypothesis is true. And so when we find our probability, when we find our test statistic, and we're saying, ooh, our p-value is super low, we're using that distribution and saying, see, if we got this, if this is unlikely or if this is likely, it should be here and it's way over here. Probably not likely or whatever. Anyway, so we're using this knowledge to find the probability, and that probability is what allows us to determine if we're going to reject or retain the null hypothesis. So that's just kind of a refresh / maybe hearing it for the first time / oh my god, I totally forgot all about statistics as a whole. Crap, I forgot we had to do that, whatever. But this is just a bit of a refresh for null hypothesis testing and what it means for research methods. Now that you're actually applying these concepts to your own research itself, suddenly knowing the statistics, suddenly knowing what it means to say you're rejecting or retaining null hypotheses, now we know, oh, p-values, you know what that, It's good to have an idea of what the hell it is you're doing with these numbers before you start analyzing them in regards to your own studies.